Grade 11s, we're on our 4th day of sequences and series, and we're going to talk about rules to define sequences today. A sequence has a general term if an algebraic rule can be found to generate each term. So if a sequence is arithmetic or geometric, which we've looked at, then a general term can always be found. Very predictable pattern. We know how to go about finding that common difference or common ratio and writing the general term. But for any other type of sequence, it is not always possible to find a rule for the general term. So we're going to look at some today that are neither arithmetic nor geometric and determine rules for them if possible. Given the sequence 1, 8, 16, 26, 39, and so on, determine the next 3 terms. My strategy would be to look first and see if it's arithmetic. I'm going to quick look and see also if it's geometric. Between the first 2 terms, I would be adding 7. Between the next 2 terms, I would be adding 8. And then I would be adding 10, 13, and so on. It's not arithmetic. It's not following the same difference every time. Let's see if it's geometric. Between the first 2 terms, I would be multiplying by 8. Between the next 2 terms, I would be multiplying by 2. It's not exactly geometric. I did notice something, though, as I looked at the arithmetic differences. They seem to follow a pattern. So I'm going to continue with these differences between my first 2 terms. So T2 take away T1. I noticed it was adding 7. T2 to T3, sorry, T3 take away T2. Difference was 8. T4, T3, T5, T4, 7, 8, 10, 13, from 39 to 56 is 17, and from 56 to 78 is 22. I think I'm seeing a pattern there. It would probably be better for me if I organized it in a table. So my term, first differences. I'm going to look at second differences. See if I can come up with a relationship. Term 1, 8, 16, 26, 39, 56, 78. Just for the sake of my eyeballs. My first differences were 7, 8, 10, 13, 17, 22. My second differences between 8 and 7 is 1. Between 10 and 8 is 2. Between 10 and 13 is 3. 17 to 13 is 4, and so on. So I have found a pattern in the second differences. There's going to be no pattern in the ratio. So if I want to find my next 3 terms, I'm going to extend my pattern. So 6, 7, 8 is my pattern. And I'm going to work backwards to my first differences and then my terms. If I can do this somewhat neatly. The difference between 22 and the next term will be 6, so it would be 28. And 28 and the next term would be 7, so it would be 35. and 35, and the next first difference would be 8. So that would be 43 for my first differences. The difference between the term value 78 and the next term is a difference of 28. So 78 and 28 is 106. Between 106 and the next term's value is a difference of 35. So that's 141. And then the next first difference would be 43 is 184. So my next three terms should be 106, 141, 184. Let's try another one. 5, 14, 41, 122, 365, and so on. I want to find the recursive formula that would allow me to generate future terms. First of all, I've got to figure out whether it's arithmetic or geometric, close to either of those or not at all. So let's look at arithmetic first of all. See if I notice any patterns or anything suspicious. Between the first two terms, between the 5 and the 14, there is a difference of 9. So is my common difference equal to 9? The difference between 14 and 41 sure isn't 9. Between the next two, between 14 and 41, the difference is 27. And then between 41 and 122, the difference is 81. So I'm seeing a pattern between the differences. It's certainly not arithmetic. We're not adding the same thing each time, but those differences are following a pattern. Let's organize our thoughts in a chart here. 5, 14, 41, 122, 365. Okay, my first differences between 5 and 14 is 9, between 14 and 41, and so on. 81. So the next differences is 243, of course, 729, and 2187. So my first differences are not the same, and if I were to continue, my second differences would not be the same, but I can see a relationship between those first differences. The first differences themselves follow a pattern. 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, 3, and so on. It looks like it should be a geometric sequence. We're going up by powers of 3, and yet if you do, looking at ratio, if you do 14 divided by 5, you don't get 3. You get something rather close to 3. You get 2.8. But it's not exactly a geometric sequence, but it's close. So I've noticed that my first term is 5. My second term is 3 squared. My third term is 3 cubed. Sorry, plus 5. 3 cubed plus 5. It's 9 plus 5 is 14. 27 plus 5. Sorry, I made quite a mess of this. My first term is 5. The second term is 3 squared plus the first term. The third term is 3 cubed plus the second term. Can we come up with a rule for this? So in general, our recursive formula first term is 5. Subsequent terms would be 3 to the n plus the term before. Let's check with one that we know. Make sure our formula is correct. Let's jump down to t. We looked at T1, T2, T3. Let's look at T4. We're saying our answer should be 3 to the 4 plus the value of the third term. So that would be 3 to the 4 plus the value of T3, which is 41. 3 to the 4 is 81. 81 and 41 is 122. In the example section of your textbook, they have done the same problem but did it in a different way. They came up with a different recursion formula. You can compare the two if you wish. Let's look at a different one. This one has fractions in it, our favorite. Given the sequence, 3/4, 5/9, 7/16, and so on, determine the next two terms and the general term. When I look at this, I notice that it's progressing in a regular sort of a way. But I am also looking at the numerator and denominator separately, and that is a good strategy when working with these. Numerator and denominator. I can see that the numerator is going up in an arithmetic pattern. So my numerator is going up by 2's. And the initial value is 3. So I can come up with a pattern for the top, and my next two terms, therefore, would be 13 over something and 15 over something. The bottom isn't quite so easy. We'll come back to the numerator in a second, but the denominator is certainly following a pattern. It's following a pattern of really pretty squares. So 4 is 2 squared, 9 is 3 squared, and so on, so that I know my next two terms will be 49 and 64. Okay. On the bottom, for term 1, so 4, 9, 16. For term 1, it's 2 squared, 3 squared, 4 squared, and so on. So we're a little bit displaced. So on the bottom, it would be n plus 1 squared. And on the top, it would be 3 plus n minus 1 times 2 from an arithmetic sequence. So putting that all together, the general term would be the tops 3 plus n minus 1 times 2. Now I could tidy that up. That would be fine. And on the bottom, it's n plus 1 squared. And n cannot be a real number. It's a natural number, which means not including 0, 1, 2, 3, 4, 5, and so on. Page 439 gives you some to wrestle through. Good to work with a friend.